Yeah, hi everyone. Thanks for coming to my tutorial. Let me begin by briefly introducing myself, and I want to keep it short and concise, so I basically compressed all my CV into one long word. My name is Andrzej Warzynski. I'm a compiler developer at ARM. I've been working with LLVM for roughly 4 years, mostly downstream, so I'm not really familiar to most of you. I also worked with LLDB and even presented a tutorial on LLDB debuggers to this audience in the past. However, my original background is in scientific computing and mathematics, so I'm still relatively new to compilers and LLVM in particular. Last but not least, I live in the lovely city of Glasgow in Scotland. I'm not Scottish, but I do consider myself an aspiring Highlander. This tutorial is about writing LLVM passes. It focuses on out-of-tree development. Reason being, it gives you a nice isolation, and we can focus on the problem we're trying to learn about. And even if you work in tree, I think it's still relevant because, again, you focus on the stuff that's important right now. All the examples that I'll present, I've tested them thoroughly on Linux and Mac OS. This stuff in principle works on Windows, but Windows is a bit special, and I'll give you some hints. I wasn't able to test everything on Windows. I will only talk about the new pass manager. If you don't know what that is, I'll introduce it. And we'll only look at middle-end passes, meaning that I will not do anything specific to any of the LLVM backends. This is targeting beginners. If you're already familiar with this content, I hope there'll be something that you don't know yet. And if that's not the case, please stay, because somebody needs to answer all the difficult questions at the end. Last but not least, this is meant to complement a project that I set up on GitHub called LLVM Tutor. So all the code examples are available on GitHub. There's much more than on the slides. If you get lost in slides, some of them are a bit dense, and I apologize for that. I'll try to emphasize what's important. If you get lost, there are links in the slides. You'll have access to them afterwards. Everything that's blue on the slides is a link. So you can go and click and read at your own time. This is the outline. The idea is basically to cover the full workflow. So we'll start with your background, what you need in order to start developing, and some background information. And then we'll jump into your first pass, Hello World pass, focus on CMake setup and all the skeleton that you need to implement in order to have your first pass. Then we'll look at some more interesting examples, a transformation pass, an analysis pass embedded into a standalone tool, and also testing, because I think that's important. And yes, integration back with LLVM, because we focus on out-of-tree development, but sometimes you want to integrate things back into LLVM. So let's start with the setup. Nice thing about working out of tree is that you don't have to clone the sources, and you don't have to build from sources. There's pre-built packages available for macOS and Linux, and you can just download them, which is brilliant, because I think building can be sometimes daunting if you're just starting with a large project. If you're on Windows, you do have to build from sources. Even though there are packages available, they're not suitable for this sort of development. So you do have to build from sources, and you do have to, and I apologize, I'm choosing just one screen, but I have to choose one of them. You have to use this CMake flag when building, which is specifically for building plugins on Windows. And we are building plugins because basically we are writing passes, we'll be building shared objects based on them, and those are our plugins that we will be loading dynamically. That's what we want to do. Now, before we can introduce a pass or what it is, we have to decide which pass manager we want to use. Because LLVM has not one, but two pass managers. There's the legacy pass manager, which is currently the default pass manager. And there's the new pass manager, also known as pass manager, soon to become the default pass manager. I will not compare the two of them. There's previous talks, and I think it's just best to go and watch them because they dive deep into the matter. I will emphasize that the official documentation on LLVM website on writing passes is still based on the legacy pass manager. So I figured that it's more interesting to just do the new pass manager. And last but not least, the new pass manager is implemented using a lot of nice C++ templates and patterns like curiously recurring template pattern, mixin pattern, concept-based polymorphism introduced by Sean Parent in one of his famous talks, in which he also claims inheritance is base class of evil. These things are important and very interesting, but you don't have to know them in order to follow this talk. We'll go a bit higher level. If you go into reading the source code of Pass Manager, this is something that's very relevant and you want to study it, but you don't need it, just for this tutorial. I'm also emphasizing it because there's plenty of comments in the implementation of the Pass Manager which refers to those paths, emphasizes how important they are. Right. So we can finally introduce a concept of a pass. So pass is simply something that operates on a unit of IR. I will introduce what a unit of IR is on the next slide. For now, because we decided on the new Pass Manager, we'll split the passes into transformation analysis. That's basically the split that's implemented there. And I think it's fairly self-explanatory what the difference is. Transformation will take a unit of IR, change it, transform it, and you'll get something new. Analysis just looks and generates some high-level information based on for the unit of IR. Now, in terms of implementing, transformation pass will be harder because you have to change code and you have to produce something that's equivalent to your input in some sense of equivalence. So that's trickier. Analysis in this respect is a bit easier, but there's interesting interplay between the two because normally you have a transformation pass which requests results generated by analysis pass, and that triggers that analysis pass being run, right? So you first have your transformation pass, and it requests some results of some analysis, which means you have to track because if that analysis pass was already run, the results are cached, so you just get the cached results. So the Pass Manager, which just manages all this, has to decide, okay, do I have access to those results, or do I have to generate them from scratch? So that means that managing analysis passes is harder than it is for transformation passes. The good thing for us is that we're only implementing passes, so we don't have to worry about it today. Now, we need a unit of IR on which we can actually run our pass. So I like to reason about code in terms of C. So I usually start with a C file like this one at the top, which has just one function, foo. You want to use clang to emit LVM IR code for it, so you just pass -emit LVM. You also want -s to make sure you work with textual form as opposed to bitcode form, and that will generate you this file. The interesting bit is the bit in the purple, which is function foo that corresponds to the function at the top. Everything else is some metadata, which for the purpose of this presentation, you don't have to worry about, and we will not. What's interesting about this file is that the whole thing is a IR module. IR as an intermediate representation, which is what LVM uses internally to reason about your code. So the whole thing is a module. This module is fairly basic. It contains only one function, foo. Function is also a unit of IR. And this function is also fairly basic because it contains only one basic block because there are no jump or no branches. And these are 3 units of IR. Module, functions, and functions contain basic blocks. And then basic blocks contain instructions. And that's all you need to do in order to follow this. Finally, we need something to use our passes to load them. And for that, we'll be using opt. Opt is a LVM's module optimizer. It's your favorite tool. It has plenty of command line options. It's very powerful. It's basically your compiler stripped of a lot of the driver stuff and other things which we don't really care about for the sake of this. The way it works, you normally provide an input file, an IR file, and then you either transform it or you just analyze it and it'll always output the IR file. We will be loading plugins, so that's what we will use. Now, as I mentioned, plenty of command line options. One of my favorite ones is dash.cfg, which basically will generate you control flow graph files, which are amazing for debugging and also trying to understand what's happening internally with an LVM. So that's something that's really worth bearing in mind. And yeah, analysis will often be printed into standard output, like here. So that's something you want to really, really familiarize yourself with. Right, so that was just the background. So you know where to get LVM from, you know how to generate input files, and what tool we'll be using. So we want to write our first pass, and this first pass is not particularly exciting. All it does, it will visit a function, print its name, and print the number of argument a function takes. But it's very good at illustrating how to do it. and I'll be using only the new pass manager. So the bit on the left is from the project I set up on GitHub. The bit on the right is from LLVM for reference. So visitor is the main function that does the heavy lifting, as in visiting the function, printing its name, and the number of arguments. The pass itself, it's called hello world, and it inherits from pass info mixin. So you have your mixin pattern. It's a template class, and the template parameter is the same as the derived class. So that's your CRTP idiom. What you have to implement is a run method, which takes a unit of IR on which you want to run your pass, as well as the corresponding analysis manager. You pass the analysis manager because you may want to query it about some results. I don't, because this is a very basic pass, so I don't really care. I'm not giving it a name because I'm not going to use it. Finally, what you have to do is return an object of class preserved analysis. That's a new pass manager thing. So I'm only calling a static method within that class called all, and that corresponds to return a set of analysis corresponding to everything that you're currently managing. Because I'm not changing anything, so I'm just using that because it's easy. I don't have to do anything fancier than that. Now, question is, how do I know I have to do it? Because there's no official documentation explaining, right? So as an aspiring compiler engineer, you'll go to the source code and try to understand. So you go to passmanager.h, which implements the new pass manager. You check pass info mixin, which is our base class, and you discover it's very basic, and all it contains is one method name. So it doesn't explain why I implemented run. So you go further down, you check the pass manager itself, and you discover that it also inherits from pass info mixin, which is very nice because it means it's also a pass, which makes a lot of sense because all pass manager does is aggregates passes and runs them over a unit of IR. So it fits into this concept of a pass. Easy. So you find run method, takes a unit of IR, analysis manager, and then you check there's a for loop that goes over all passes that it aggregated, calls the corresponding run method on the unit of IR, analysis manager, collects the preserved analysis, and then invalidates them in the analysis manager that it has access to. And this is nice. Obviously, I extracted bits, comments, and other things from the source code, and I highlighted stuff that's relevant to me. But if you go to that source file, you'll see those lines, and it's very obvious what's happening, which I think reflects nicely on the design. Still, it doesn't explain why I have to implement the run method. So you check the actual vector that contains the passes, this one, and you check what it contains, and it's a vector of objects of type pass concept. And that's your concept-based polymorphism. If you check the source file, it explains in the comments what it basically boils down to. A class fits into a concept of a pass if it implements this run method. And that's your concept-based polymorphism. There's no C++ semantics to express that per se. And that's it. We are done. We implemented our pass. We have to register it, because we'll be using opt to load it and to use it, and we have to tell opt somehow how to do it. So for that, and it's all happening in the same source file, for that you implement a method called LLVM pass plugin info. And that method returns an object of type pass plugin library info. You check what that is, and pass plugin info, and it's fairly simple struct. It contains API version, plugin name, plugin version. It all makes sense. And there's this last thing, which is a callback that takes PassBuilder, and it's called register PassBuilder callback. PassBuilder is something that connects everything together. And what we need to do is register the callback that tells PassBuilder how to create our pass. So I'm creating it here. So I'm basically redirecting this to this method. My callback is called pbhook. I check my pbhook, and it's basically pb, which is PassBuilder, and it's register pipeline passing callback. This callback will be used when PassBuilder is passing pass pipeline. Pass pipeline is simply a list of passes you want to run. It's something that we'll specify on the command line when running opt. So this basically tells the PassBuilder, OK, when you're passing that pass pipeline, use this hook. And all it does, it checks the name of the pass currently being passed. If it's hello world, great. I want you to run this pass. It adds it to the list of passes to run. You may want to, you may be curious to see where this is actually being used. So you go to opt, new pass manager driver. You see a method called run pass pipeline, exactly what we're after. You see that there's a loop that goes over pass plugins, which are plugins that I specify on the command line to load, not run, to load. And then it calls for each one of them this method, which is exactly this one. There's a different in caps because there's one level of indirection, but otherwise it's this method. Again, we're almost done. In practice, this is how you'll register. So instead of having multiple hooks, you'll just fold it into one method and have a bunch of lambdas, which looks a bit hard to read. But why would you need a separate function if you can have a lambda? One last thing to mention is that you might be tempted to fold this into this method. And that will work fine for what we're trying to do just now, because we were loading things dynamically. But towards the end, when we try to integrate things back into LVM, it will make sense to keep them separate. So I keep them separate just for now. So that's the implementation. You still need your CMake script. And I think that can be also a bit daunting. But as a matter of fact, there's not much going on here. And there's, I think, key 3 things that you have to do. You have to point CMake to where your LVM is installed. And I'm focusing on LVM 9, the latest release. So I'm doing it here. I'm basically updating CMake prefix path. So internal set of paths that CMake is tracking with the stuff that I pass out command line when I'm building my project. Because when I run CMake, I do have to specify where my CMake is installed. There's no other way. So I'm just teaching CMake, OK, this is where to look. Next, I use find package, which is a standard CMake thing of saying, like, OK, I want you to find LVM9 because that's what I want to use. I told you where to look there, and load the configuration. And this is something that you want to use. You can bypass it and do things manually, but you don't want that because this gives you access to the configuration of your LVM installation and makes a lot of things easy. This example is relatively not that involved, but once you start complicating things, then it's trickier. And in this particular case, I'm using it to include directories from LLVM because I'm including stuff from LLVM, and I want to know what the path is. So I don't have to do it manually. I just use find package. Last thing that you have to do is add library, which is a standard CMake way of defining a library. I'm defining it as a shared because I'll be loading it dynamically. The name is hello world because that's the name of our path, and just one source file, and that's it. And you're pretty much done. There's a few gotchas. There's always going to be gotchas. The 3 that I identify for this particular file is on macOS, and I'm using macOS. Clang defaults to C++98. LVM is built using C++14. So you have to change the standard that you're using. The other thing is that you might be tempted. So I use just add library. But if you go to LVM source, you'll see that they use add LVM library. And you might be tempted, and you'll be asking, like, how come? Maybe I need to use that. What's so special about it? The thing is, no, you don't have to use it. We just want very basic shared objects to load them. Add LVM library when you want to integrate things back into LVM. But we're not doing that just yet. It's also relevant if you're building your plugins on Windows, because Windows is a bit special. But I think I'll just leave it here. If you care about Windows, I'm happy to have a chat about it afterwards. Last thing is that our shared objects refer to symbols in LVM, but we're not linking anything back, which is fine because we're loading things dynamically into opt, and opt will contain those symbols in its memory. So you're fine. And linkers on Linux will not complain. Linker on macOS complains. So you need this special flag, and that's it. Right. So now I'll try to demonstrate this. Are there any questions? I forgot to mention, I don't mind being interrupted, so feel free. Right. So, okay. Right. So this is where I cloned my project. It contains a bunch of things, but hello world example is in a dedicated directory, hello world. So I'll just build that one. I need to export my LVM installation and build. Right. We need a file to run our pass on. So I'll start with a C file because that's what I find easy to reason about. And I mentioned that hello world basically visits a function, prints its name, and the number of arguments. So I have 3 functions, different names, different number of arguments. So I need to generate a IR file, and I'm ready to run my pass. Now, I need to load the plugin. So load pass plugin, it's the new pass manager way of loading it. And I need to specify pass pipeline. Again, new pass manager thing. You specify pass pipeline. And new pass manager is very explicit about it to the point where I say I want to run 2 passes. Hello world, because that's the one I just implemented. And hello world, again, twice, because I want to try things. And I'm disabling output because this pass doesn't really change the IR module, so I don't really care about the output. So this is the way of doing that. And voila. I've barely written any code, yet I have a fairly deep insight into what's in my input module, which I think is amazing, which I think showcase how powerful LLVM is. And it's something I really like about it. And you can see it prints, the result is correct, and it prints it twice for each function because we requested it to be run twice, right? That's the pass pipeline that we requested. That's it. That's it. You have your first pass. Yeah, if you have any questions about this one.
Do those passes run strictly sequentially? Because I would expect it to say foo bar fez, not foo foo bar bar fez fez.
It's a function pass, right?
Oh, a function pass.
So it's,
yes.
Yeah, for each function, the pass pipeline is hello world, hello world. OK. So this first one, I think it was nice to showcase how not difficult it is to write a pass and run it, and to learn something about your modules. But it didn't do anything exciting. The second one is much more exciting, and it actually changes something. It's a transformation pass. What it does, it takes additions, 8-bit additions, and replaces them with this really, really weird and a bit nasty formula. I took the formula from a paper on obfuscation. I found it interesting, and I figured it's a good example to showcase. What we have to do is go through all instructions in your input module, check whether it's a addition, then check whether it's a 8-bit addition, and only then construct instruction that corresponds to this and do the replacement. I will be using IR Builder to create instructions. IR Builder, which is a very powerful API available in LLVM and relatively easy to use and well documented, so I recommend using that. Once I construct the new instruction, I'll just use replace inst with inst to replace them, and that's pretty much it. This is the main implementation. The method, so the pass is called MBA add. MBA stands for mixed Boolean algebra, and you'll see these formula in mixed Boolean algebra. Add because it deals with addition. The main method is called run on basic block. It's just an implementation detail because I want to reuse the same implementation for the new and legacy pass manager. The legacy implementation is available on GitHub, but I want to reuse the same implementation, so I'm just using run on basic block. Otherwise, there's nothing to involve in there. What the method does, it simply goes over all instructions in your basic block, checks whether it's a binary operation, checks whether it's an addition, checks whether it's a 8-bit addition, and does all the cool stuff on the next slide, because I couldn't fit it on one. There's two more interesting things on this one. One is LLVM debug, which is LLVM's debug stream, which you can use for debugging, which is very powerful and very useful. What this one does, it simply prints a current instruction and the new instruction that you're gonna replace it with. And this is something that allows you to avoid printf or commenting things out and changing stuff between debug build and release build. You also have this subst count, which is simply an integer that tracks how many substitutions we do, which I'll also use later at runtime. And this is just the substitution, well, creating the instruction, because it's a bit weird. This is not the prettiest bit of code, but it does what it does. Basically, you need these constants in the expression, and then you just construct your instruction by chaining multiplication, addition, XOR, and what's not. There's nothing too involved happening there. And once you're done, then you just call replace inst with inst, and that's it, which is brilliant. There's few things left. So I mentioned LLVM debug. You gain access to that by specifying debug type macro. It's all in the same source file for this pass. So you define this macro. You define it as something specific to your pass, because obviously every pass will have its own, so you have to do it something specific to yours. Once you have that, you can use -debug only equals MBA add. MBA add comes from here. And we'll use that when running opt. And you use debug only because we want only output from this pass. If you skip debug only and you use just -debug, then you get output from all the passes that you run, which is something you may want to avoid. The other thing is this integer that I mentioned that tracks the number of substitutions that we do. You enable it by defining this macro, and you print the actual contents of this by passing -stats. And these are all options that opt takes. So quite powerful tool, isn't it? So yeah, let's see this one in action, because it's much more interesting. So this time, let me do it again. So this time, all the remaining passes, they live in the main directory, split into lib, include, test, and whatnot. So I'm going to build the whole project from scratch. So again, exporting the installation of my LLVM, CMake, Ninja. And I can check. So the lib directory contains all the passes and all the plugins that I implemented. I only really care about lib MBA add, right? Because that's the one we will discuss. We need input files. So for this one, I'll start with 8-bit addition. So it's the main function is foo, which takes 4 arguments, 4 8-bit integers, and adds them together and returns the result. It's all wrapped in main because that will allow me to test a bit more, and I'll show you in a minute or two. So we need to generate a IR file again. And we are ready to run our pass. So again, loading the pass, the plugin, specifying the pass pipeline, and our input file, which we just generated, which is 8-bit addition. And now you want to see what happens, or whether we've done anything interesting. So you can see, so it's an IR module. There's a lot going on, but the really interesting thing and relevant one is function foo, which does 3 additions. And that's what we really care about. Now, if we check the output file, boom. Yeah? So that's our function foo, which now contains a lot of instructions, which we just injected. And if you look carefully, you'll see the constants that I created that were present in the formula, and also you'll see basically the same pattern 3 times, because it's 3 additions and it's the same pattern. So I know, I'm confident that my pass did run. But what happens if the addition is 32-bit? Because the formula doesn't work for 32-bit additions. So I don't want to apply it. So recall that there was a check in the implementation to verify that it's only run for 8-bit additions. So now I have similar file, but it takes 32-bit additions. So it's exactly the same example, but it's just the type of the input argument is different. So generating the input IA file again, running opt, loading the pass, specify line, and generating the file. So let's just look at the output file. Again, worked. Nothing changed. So it's exactly the same 3 additions that I had in the input module. So they work, which is a great test, right? Because that's exactly what you wanted to see. One last thing that we want to check, and that's the reason we added a main function, is we want to run the output file because, oh, yes, that makes sense. Because we do additions, and I created some really funky injected some funky instructions, but how do I know they're correct? I need to check that. So let's try with the input one. So that's the add 8bit.ll is the input file, basically translated into IA. So I run it, and I pass 1, 2, 3, 4, and I expect the output to be 10. Yeah, makes sense. I do the same for the output file, which contained all the weird stuff. Also 10. So I've verified it works, which is important, right? We don't just want to hack stuff. We need to verify it works, which we just did. You can also try the one with 32 bits. It also gives you 10. And finally, we may want to check debug only and stats to see what happens when you use those. And there you go. The only difference from what I was doing before is by adding those dash stats and dash debug only. And you have, this is debug only. It tells me original instruction, the new instruction, excellent for debugging. And I'm controlling that at runtime when I run opt. And also the statistics. I'm doing 3 substitutions. It all makes sense. And again, I didn't really write that much code. And I changed the file completely, which is, I think, amazing and shows you how powerful LLVM is and actually how quickly you can do really interesting things. Right. But that was a transformation pass. And I mentioned there's a split into transformation and analysis passes. So far, we only looked at transformation passes. We know how to build them. But now we want to learn how to do an analysis pass. Now, I will complicate a bit. I won't just implement an analysis pass. I will create an analysis tool, a standalone out-of-tree analysis tool. So I'll embed an analysis pass inside a tool, because that just makes things a bit more harder, but also more interesting. I'm going to create a tool that I call static. Static as opposed to dynamic. Static because it counts static calls, dynamic being runtime, static being compile time. So what I want to write is a tool that takes a file like this one and will print me a summary of what are the static function calls. Now, bear in mind that until now we've been using IA files as our input, and that stays the case. So there's one step missing. You have to take this file and generate input LL based on it. I simply put C file here because that fits on the slide. IA file wouldn't. I will be using a command line API from LLVM, which is super powerful, which is very well documented, and I encourage you to use it. Now, finally, static basically wraps around an analysis pass that does analysis of this module. You need a transformation pass that will request those results from that pass, because otherwise, how do you trigger the calculation? Finally, you need a main function and a main file that will glue everything together. So you need 3 components. So that's what's new, on top of the fact that we will be doing analysis pass. The pass is called StaticCallCounter because it counts static calls. It inherits from analysis info mixin. That's different from transformation passes. The 2 previous passes, they inherited from pass info mixin. This is analysis info mixin to highlight this is analysis. And it's the same story. So it has template parameter, which is the same as the derived class. You have to implement run method, which takes a unit of IO on which you want to run your pass, the corresponding analysis manager, and you return result. Because this time, you're generating a result. So you're not returning the set of passes or analysis that you preserve, because you're not going to change anything anyway. What you're interested in is the result that you generate. And you, as a developer, you define what that result is. So in this case, it's just a map that simply maps function and the number of times that function was called. Simple as that. You also have to provide this analysis key, which is used for identifying your analysis pass. So bear in mind that we will be requesting results from this pass. Then those results will be cached. Then some other transformation pass may request them. So the analysis manager needs to keep track of that, needs to be able to connect these results are coming from that pass, and they are valid, or maybe they're not valid. So it needs some mechanism to track them. So you have this analysis key, which is also a new pass manager thing. What's important about it is that the value doesn't really matter. It's the address of this value that's important. And again, you may want to go to Pass Manager, check what analysis info mixin is, and you'll discover it's a fairly basic class which has only one member function called ID. And that returns the address of the key. It's worth highlighting because it's called ID, but it's returning key, so it's a bit confusing. But you'll see ID being used in many places. So it's worth bearing that in mind. Right, so that's just the surrounding bit. We have to implement run on module, which is the function that actually does the interesting stuff within our pass. Again, run on module, its implementation details, so I can reuse the same implementation with the legacy pass manager implementation, which is on GitHub. So run on module simply visits all instructions and checks whether it's a call instruction. And if it's a call instruction, it'll just increment the corresponding counter in my results map. Nothing really too involved happening there. What's really nice about this example, and what I like a lot, is these 3 loops, one after another, which is quintessential LLVM, and which is such a broadly used LLVM idiom, and it's beautiful. It's beautiful because we start with a module, and we want to iterate over all instructions, and we have all those iterators implemented for us, and it's just so easy, yeah? Because I'm not really doing that much, which is fantastic. But otherwise, that's it. That's the implementation. We need a transformation pass that will request the results. So I'm just calling it StaticCc wrapper, as in StaticCallCounter wrapper. It's a transformation pass. We already know how to implement them. We know what they need to inherit from. Again, I need a run method that takes a unit of IO on which I want to run. And I also need a module analysis manager. This time, I will be requesting results. So I am using a name of that. I am adding a name when defining the function. And I'm requesting the result by just calling getResult on the module analysis manager. And as a template parameter, I'm passing the analysis pass from which I want to get my results. Print StaticCc result is just a function that prints the results. Nothing too special about it. Again, I'm preserving all results because I'm not changing anything. I'm not making any modifications. It is a transformation pass, but I'm not really transforming anything. Now, you might be tempted and you might be interested, what if I am changing something? What do I have to do? So you just call abandon, which is a method in preserved analysis. Abandon is not a static method, so you have to create an object of this class and then call the method. And you simply pass as a template parameter, again, the pass for which analysis result you want to invalidate. Now, we don't have to do it because we're not changing anything, but it's an interesting exercise if you want to do it. Try this, run your pass StaticCc wrapper a couple of times, fire up your favorite debugger, and you will see the stuff being recalculated. But otherwise, we don't need it just for this pass. We need a main function. So that's the third building block. Again, this is not very complex. There's not really that much going on. We need one input parameter, input module, which is basically the IR module that we'll be running our pass on. And I'm using LVMCL command line API to pass it. You pass the command line options at the top. Then pass IR file, which is just one API call, and I have my module already available for me to play with. Otherwise, a few other things like, I don't know, LVM shutdown object, which takes care of cleaning the memory, because we'll be pulling things from LVM, and we want to make sure that we don't leak anything. But otherwise, it's just making sure that M was, the module was correctly read. And we go to count static calls, which is the interesting method that does the heavy lifting for us. So this one is interesting because we have to do all the things that originally opt did for us behind the scenes. Now we have to do it ourselves. And it's interesting because it helps you to understand how things work and how they're connected. So one thing that we have to do is define module pass manager, because now we have to create one. So we are creating one. We're adding our transformation pass that requests the results, StaticCc wrapper, and we're just adding it here. We have to define module analysis manager. Again, we're not getting that for free. We have to define one and register our analysis pass. And this time you're passing a hook that shows, defines how to create your pass. My understanding is that you pass a hook, post a pass, because you may decide you don't need this pass, you don't need this result, so you're not creating the pass. That's my understanding, but don't take my word for it. Check the source code to be sure. You need the PassBuilder to connect everything together, and you register module, so module analysis with the PassBuilder, and PassBuilder will just glue everything together and create the required passes. And finally, you just go back to your module pass manager. You call run. It's a pass, so it has a run method. It takes a module on which you want to run your passes and the corresponding analysis manager, and that's it. You're done. We're finished. That's our implementation. There's one interesting thing that I wanted to dive a bit deeper into is the bit with the PassBuilder. And it's just a digression, but I think it's interesting and tells you how things are connected and work inside the LVM. So that's what we did in static main CPP. If you go to PassBuilder CPP and you want to check what's happening, you'll see the corresponding method, and you'll notice that it includes this pass registry def, which is a thing in LVM that contains a list of passes. One nice thing about it is that it separates the list of passes predefined in LVM from the implementation that uses it, separation. And the other thing, all it does, it goes over those passes and calls this method, right? So it first defines the macro and then includes the passes. So stuff defined here will be basically calling this method, this macro. And this is exactly what we did with our StaticCallCounter. So that's exactly the same thing we did with the StaticCallCounter, but just uses those predefined passes. And if you're really interested and you want to dive a bit deeper, you can check the list of the passes. And the one that's particularly interesting is this one. That's the one that does most of the connection and initialization behind the scenes. The other interesting thing is this loop here, which goes over module analysis registration callbacks object. It's a aggregate that contains stuff that was added when you called stuff like PB as in PassBuilder, and register analysis registration callback. It's interesting because if you recall the Hello World example, and I was mentioning how to register your stuff, there was a hook which basically called PB register pass pipeline passing callback. So I was registering my Hello World when pass pipelines are being passed. Now, this is using some other aggregate that contains stuff that I want to be run when I'm registering analysis registration callbacks. And there's a few of those aggregates inside implementation of the new pass manager ready for you to use, and you use them depending on what's your application. I'm not using it for this example. I'm just showing the implementation and what's there in LVM available for you. Now, just to quickly showcase this tool, which I already have. So it's already available. So there's dynamic and static because If you go to GitHub, there's also the dynamic version, which we won't have time to look at, unfortunately. So what I want to do is, I believe, yes, I need to generate the file first. So, yep. So that's the file we want to run. So that's exactly the same file that we had at the very beginning, the very first slide for this part. And yes, I'll just generate an input file based on that and run static on it. Voila. So the result is correct. Unfortunately, it's not able to recognize that foo is being called 10 times inside this loop. Yeah, well, there's only so much you can do. But otherwise, this is a out-of-tree static analysis tool. Admittedly, a fairly basic one, but we didn't have to do that much to get there, which is very nice. So yeah, so that's your analysis tool. The other thing that you may want to do is integrate things back with LLVM. So we've been using opt, and we've been loading things dynamically into opt. But you may get tired of it, and you may want to just be able to have your stuff inside opt or clank or backpoint or some other tool. So it's to understand what's involved, it's worth taking a step back and realize. So what we did, we took opt, we built our pass, and we loaded it dynamically. So probably there was some DL open behind the scenes doing this stuff for us. What we want to do instead, we want to have our pass linked statically into opt. Now, so that will guarantee that I don't have to load stuff dynamically, and it's always run when I run opt, maybe with -01 or -03 or something else that you care about. But doing this is not easy. You have to go and change CMake that corresponds to opt or clank or whatever you care about. And that's very involved. I don't have like clear idea. Oh, well, yes, no. But it would be nice to have a mechanism that does it for you automatically. And people doing polyhedral optimizations, they have that in LLVM right now. So recently, StaticCallCounter, he extended that to any plugins. He uploaded a patch. It's available on Fabricator. It's under review. It waits for your +1. I read it, I reviewed it, I tried it. It works out of the box. So basically, it just hooks everything into opt or clank or whatever you choose. And it's very clean and it's very obvious. And it was a lot of effort. So yes, please go and +2 it if it's something you care about, because I think that makes LLVM so much easier to work with and use and so much more fun. In order to use, once that patch lands in LLVM, fingers crossed it does, the way you use it, so when you build stuff, you have to pass extra CMake flag. In this case, it's LLVM by link into tools. By is example pass, transformation pass that Serge uploaded with his patch. By as opposed to hello. This hello example in LLVM, he created by. So you have to specify the name of your pass that you want to integrate or your plugin into tools and set it to on. When you define and CMake your plugin, you use @LLVM pass plugin. So he wrote that CMake function that automates things for you behind the scenes. Also, this highlights I used find package, so I have access to this, right? Find package as in CMake find package. That's why it's important to use find package. And otherwise, in registration, when you go to registration, this is very similar to what we did with Hello World. It's very similar. You have LLVM get pass plugin info, and then it's being redirected here. The thing is, now we want to do things statically. And when you do things statically, you want this separate method, get by plugin info. We had similar one for Hello World, and I mentioned that if you wanted, you could fold that one into here. But now you want a separate one because you want to integrate things statically. So that's why it makes sense to have them separate. And that's it. Otherwise, it's ready to use. It's really nice. But the final bit. We did some testing on the command line. I verified that the passes work, but what we really want is something more pragmatic, and we want it in our CI. And And we are out of tree, and it's tricky because we are out of tree. Now, we want to use LLVM lit. Lit as in LLVM's integrated tester, because it's super powerful, it's super flexible, it understands what compiler does and what's important and what should be tested. And we're very close to having it set up for us. So we'll be using lit tests, and every lit test is basically 3 things, and we already covered 2 of them. So we're very close to having this fully tested. So every lit test is, and this is in the context of the passes that we are developing here. So they work on the middle-end passes, work on IR modules. So your lit test will contain your IR module. It will contain a comment that starts with run, which simply stuff that we've been doing on the command line with opt. That's exactly what we've been doing. And this is used by LLVM lit, which is a tool, the test runner and test discovery tool. So it will look for this run method. So in our case, these 2 go to opt because that's what we defined. It'll generate the output module and pipe it to FileCheck as test output. So the piping is happening here. And then the third thing in your lit test is expected output, which is also a comment which starts with check, which is a FileCheck thing, and you simply put stuff that you expect to see on the output in your when running your passes on your input IR. And that's also being sent to FileCheck as expected output. FileCheck does the comparison. FileCheck is a tool that comes with LLVM. It's a pattern matching tool, which is very powerful, and it's something you really want to familiarize yourself. Documentation is available online, and it's really good. And FileCheck tells you whether you pass or fail by comparing the 2. Now, what's tricky is that LLVM lit needs to be able to find opt, FileCheck, identify what's your test. Also, our passes are shared objects, and then on macOS, shared object has dylib extension. On Linux, it's SO, and stuff like that, and it just explodes. So it's not immediate. And it's, I think, not as nicely documented as it could be. But effectively, you need 2 Python scripts. Python, because LLVM lit is a Python script, and you need to teach it where to look for your stuff and how to configure it. So it normally looks for stuff like lit site cfg.py or lit cfg. What I normally do is I have lit site cfg py.in. In as in it's input for CMake, because CMake knows where my LLVM installation is and where to look for the corresponding tools, and knows what the extension of shared objects on this platform are. So I want CMake to propagate the script with the relevant information. So I'm doing it here. For instance, extension of shared objects on this platform, locations of the tools, because again, I specified where LLVM is installed, so it knows where to look for it. And otherwise, it delegates all the heavy lifting to another script, litcfg.py. Now, this is the whole script. This is all I have in my CI, and I have this running in Travis, which I think is amazing because it makes me very comfortable about what I do. And that's it, right? It's not obvious what's happening because I'm using this config stuff and lit LLVM, and it's not obvious where it comes from. Those are global objects that LLVM lit, the Python script, will create for you, and you have access to, and you just have to propagate it, the fields that you care about. You have to propagate with the config that you care about. The litcfg.py file, so the one that does the heavy lifting, is also fairly short and does not read that much going on there, where you specify suffix of your tests. All my tests are LL files, because that's all I've been doing. You specify, for instance, this add tool substitutions is important, because in my run commands, I just write opt, FileCheck, clang, or whatever. But I don't want LLVM lit to just go and use any opt or any clang. I want it to use the one from the same LLVM installation I've been using all the way along. And that's important, right? Because you want to be consistent. And, well, this is compiler, so you do have to be careful what you use and make sure that you're using tools that match. But otherwise, there's not really much else. But just to quickly summarize, I'll show you how this works in practice. So that's, yeah. And my test directory. And bear in mind, I am out of tree. And I have a bunch of passes, and I have a lot of tests, and they all pass. And every single time I push to GitHub, it's all being tested, which, well, it makes me very, very comfortable because I do make a lot of mistakes, and I need CI. And I think this is brilliant. And I think it's a shame it's not documented a bit better. I also want to show you a test. So going back to the NBA art pass, which simply replaces 8-bit additions with this really weird long formula, and we wanted to make sure that it's only for 32-bit additions, so we need to write a test for that, and we did. That's my test. It's the input module, which is just 3 additions, consecutive additions. That's exactly what we used when we were testing on the command line. I have 2 run commands, because one for new pass manager, the other one for legacy pass manager, because I have 2 implementations on GitHub, and my expected output. I am using check next, which is a variation of check, but it basically means I want to see 3 consecutive additions, nothing in between. So make sure it's there. And this makes me comfortable that even if I make changes to my pass, I don't break it, which is I think, important, right? We all care about testing. So that was a full workflow, basically, right? Starting from setup, CMake, skeleton, transformation analysis tool, testing, integrating with LLVM. Some final hints in terms of debugging and solving problems. We are loading stuff dynamically. If you worry about not being able to debug them, don't. It just works out of the box. I use LLDB. This is how you, for instance, can break on the run method inside the NBA art pass that we've been using. That's all you need to do. Just break NBA art, : run, and then run, and LLDB will just hit that breakpoint. And you can see what's happening and look around if you're confused. I used LLI to run youâ files directly on the command line, which again, I think is a nice thing because, well, I have a tendency to forget about it and just compile everything to binary, but you don't have to. You can just skip that step, which is, again, nice thing. If you want to debug pass pipelines, and we didn't talk much about it because that's pass manager thing, but if you do want to make sure that your pass is being run or want to see which passes are being run, opt has these nice options, which I like particularly. Otherwise, the CMake that I showed you was fairly basic. I didn't do any sanity checks for a reason. I wanted to keep it clean and also fairly straightforward. But in practice, you should be doing sanity checks, a lot of them. And if you check the master CMake in my project, it's a bit longer, but I want to be confident that I'm not missing something obvious. Last but not least, I should emphasize that all the stuff I'm showing here, it's been done elsewhere. This is based on comments in the source code on LLVM documentation. I've been asking a lot of questions on the mailing list and getting a lot of helpful people back to me with answers. And this is really community effort. I'm just facilitating what's available there. So thanks a ton to the community. And also I should emphasize, I didn't mention anything about the youâ and LLVM youâ, and we've been looking at LLVM youâ code. But I think it was possible to follow without actually diving deeper. You should, however, understand what youâ is and how it works, and these are my favorite references for LLVM youâ. Otherwise, this stuff is on GitHub. There's much more. There's comments. There's more examples, and it was created to make learning easier. I created it when I was studying and learning these things, and I just wanted to share. So that's there for you to refer to. So thank you.
Thanks. Great talk. Can you touch on briefly the dynamic analysis tool? How does that work to count the functions?
Yeah, and apologies, I've been standing on that side, but it just made it much easier for me. The dynamic analysis tool, well, the idea that I implemented, and I don't claim it's the best or the most clever idea, but basically you instrument your input module with stuff that will count function calls. So every time you call a function, it calls, you inject a call into a small hook that counts, okay, I'm calling this function. And you have to do it slightly differently for internal functions and external, and you also need a global variable that tracks all of this, and then at the end, you inject print function, which you have to inject at the very end after main, There's actually a nice API for that in LLVM, which is, I think, something destructors, because stuff happening after main, that's a destructor. And yeah, and it works on the examples that I tried, so.
So hi, I have two questions. Basically, the first one is that can you briefly explain how to write passes that work on multiple functions? I'm referring to interprocedural optimizations a bit. And the other question is, let's say I write my own pass and I'd like to inject that into an existing list of passes. I want to put that in a list of passes that I get from -02. How can we do that? Thank you.
So let me answer the second question, because I know the answer to it. So if you go back, so yeah, bear in mind that we are in a bit simplified scenario, as in we are out of tree, and I'm not really integrating things back. But this is the example that Serge Galton, he uploaded in his patch. And this is something similar to what we've been doing. You have this PassBuilder register vectorizer start extension point, EP extension point callback. And this basically registers this pass, I believe, at the beginning of vectorization, which I think kicks in at 02, which means this pass is being run at the beginning of 02. In terms of out-of-tree stuff, I know how to do it for legacy pass manager, and I think it's not there yet for the new pass manager. But you can use this, and it will work, yeah? So I think a legacy pass manager had it very nicely for plugins. It had API dedicated to that. I'm trying to recall. Yeah, when you do register pass, there was some mechanism, I can't recall that. So it is on GitHub. And then when you run opt and -01, 02, 03, it will run your pass. That's not there yet with the new pass manager, which is also interesting. We are soon to switch to the new pass manager by default. But in terms of out-of-tree development, there's a few changes and incompatibilities. With respect to your first question, I honestly don't know. Maybe somebody in the audience does. Okay. No more questions?
Yeah, just one general question. So when you try to transform the IR, do you usually merge the working and the transformation together, or you work the tree, get the information first, then transform the interesting parts?
Do you mean in the standalone tool that I was doing?
Yes.
So it's this one, right?
Yeah,
so,
because sometimes when you work the tree and transform something together, there may be some kind of consequences which will break your traversal.
Then you have to, then you're responsible for doing this. So you know which analysis you break. Well, sometimes you don't, and you have to be conservative, and you just say, I preserve nothing. So you return preserved analysis : none, and then you're being conservative. But otherwise, yes, you can use this, and that will invalidate StaticCallCounter. And you can check, you can play around and, for instance, have npa run, like play with this file and have npm run twice and invalidate the static analysis results and set up a breakpoint, and you'll see that it's being calculated twice, even if the module doesn't really change. Because you instrumented it, basically. You told it, I have changed it, I invalidated it. Does this answer your question?
Yeah, I think more or less.
My question is, in your static analyzer tool, is there a way to just take the C file rather than producing the intermediate L file?
I didn't do it, and that's for a reason, because I wanted to keep it simple. You can do it, but then basically what you have to do is implement compiler invocation. Because, well, that's one way of doing it, invoking Clang to do it for you. I'm not sure you probably can do it by not calling Clang, as in like, building this command line, clang-s. You probably can just call into LLVM's API. But bear in mind that Clang, the driver, is fairly complex, and there's a lot going on. So I think it would complicate the example a lot. I haven't tried it. I'm sure you can do it, but yeah. There's one in the back.
I think there's a way to debug passes, like you output the IR in between each pass. Is there any way to just say, stop at a particular pass and tell me where all the instructions came from, like which pass transformed which instructions?
Yeah, that's a very good point. There's a mechanism for that. Stop after, and there's 2 flags. However, in this scenario, you don't really need that because we've been only running 1 pass at a time, yeah? And I think there's another tutorial tomorrow by Florian and Jessica, and they'll be covering more backend stuff, and they'll be looking into actually, more passes at a time. And I suspect they might touch on that. But yeah, it's print before and print after. And you specify where's the passes. And you often use that when writing tests for the backend as well, because that's exactly what you want to see, what happens before in between pass. But over here, you wouldn't benefit anything because there's just 1 pass at a time most of the time.
Cool, thank you.
In your example of the obfuscating the plus instruction, and you did the instruction substitution, how do you not have the iterator invalidation problem because you're iterating through a basic block? Would that operation invalidate the
Replaced ins with ins is magic. It does it for you.
Oh.
It just does it for you.
I guess I have a second question. How does the pass manager know if your pass is a module pass or a function pass? The old pass manager, I kind of recalls that it has that base class that you inherit from.
Yes, that's actually a good point. So, for instance here, when I was implementing StaticCallCounter, let me get back. Yes, so this is my StaticCallCounter. And the way I define it, the run method takes a unit of IR to run on, and I specify it as module. OK, so I decided I want this to run on the module. When I then go to where I want to use it and register it, add it to the pass manager, then I have to use the corresponding pass manager, module pass manager. But you do it, right? There's no mechanism. Well, opt will do it for you if you use opt. But here, we do it ourselves. So, yeah.
Firstly, thanks a lot for the talk. It was really helpful. I'm not sure whether this was already covered in some capacity, but is this only working with once you're already in the LLVM IR?
Yes.
And then how do you get from your
you want to
language
get
into the LLVM IR?
What
is the front end?
So you are.
Is that just specific
So you are responsible, in this context, what I presented, you are responsible for generating your IR file.
Yeah.
Yeah.
Okay, so this is only addressing once passes once you're in the LLVM IR.
Well, once you have the IR code generated.
Yes.
Yes. So it's only middle end.
Got it.
Yeah.
Yeah, that answers my question. Thank you.